So in this one, let's talk about relational databases. Now, databases in general are most critical component of any system. The way I put it is I always say database is the most brittle component of any architecture. If you know your database well, more than half the battle is won, because most response time, most latencies, most things that if it goes down, it takes everybody with it. It's database. If you solve your database problem really well, your system will be very stable no matter what, right? So in this one, let's go deeper into relational databases. Future videos will cover non-relational databases and other aspects of it. But today, like in this one, I'd like to spend a lot of time around relational databases and more importantly, ACID properties, right? Okay. So in relational databases, data is stored and represented in rows and columns. Everyone knows it. But now let me tell you a very interesting story. So always remember this: whenever something new comes up, something revolutionary comes up, it always finds its first set of application in the financial domain. So when computers were invented, the first set of programs that were written were all accounting programs, right? So what happened? Earlier, people used to do accounting on sheets of papers, which were literally arranged in rows and columns, exactly how our Microsoft Excel or Google spreadsheet looks like, exactly the same, right? People used to do accounting on that. So when computers came in, the first set of programs that were written solved ledgers for them. Ledgers basically Excel and spreadsheet. Right? So you would always find this: whenever something revolutionary comes up, it always finds its application in the financial domain. Let's start with that. When computers came up, financial problem. Internet came up, payment systems were the first ones that were built. Banks went online, the first thing. Databases were built to cater to those needs. When blockchain came in, the first set of applications were cryptocurrency, doing money transfer. So you see something revolutionary comes up, it would always find its first set of applications in the financial domain. So, which means that when databases were first created, they were created to solve the problems of financial systems. So which is where you see the way ledgers were run on sheet of paper were exactly how our databases were modeled in rows and columns, right? And given that now the information was digitized, earlier it was sheets of papers where people used to do accounting in those rows and columns, are now in computers, in databases, not get connected to internet per se, right now. When the computers first came, there was no internet. Still, isolated setup of computers had those small databases where people connected and get it done. Like, so small networks were created, not massive internet per se, right? So which is where the first set of databases that were created for the sake of financial systems. So which is where, because they handle financial data, the kind of properties also that the databases provide were related to ensure that financial systems work just fine. Which is where you see that they needed data to be consistent, they needed data to be durable, they needed high integrity between data. We'll cover all of them in detail, right? They needed constraints to ensure that they needed everything to be in one place. Which is why you see these are like very common traits of relational databases, right? So we'll go into ACID properties that relational databases provide and how and what each of those guarantees, right? And this is the heart and soul of why most people pick relational databases whenever they need quote unquote transactions, right? So let me talk about it. So in relational databases, we have something called as transactions. Transactions are atomic unit of work. We'll cover ACID in very detail in the coming sections. But the transactions are something that helps us build systems which are correct. They help us build applications logic which is correct no matter what. The reason relational databases are famous is because they give us ACID guarantees. Now, name sounds fancy, but that's what it is. A for atomicity, C for consistency, I for isolation, D for durability. Now, let's talk about each one of them in depth. First is atomicity. Atomicity implies that all the statements within a transaction takes effect or none of them takes effect. So the idea is that, let's say in my financial system, if I were to insert data in two different tables, I can wrap it in a transaction such that either both of them happens or none of them happens. It would never happen that I made entry in one table, but before I was able to write in another, my system crashed and I am now having an inconsistent state. Right? This is what atomicity is all about. That no matter how many statements I run in my transaction, either all of them would be executed or none of them would be executed. Right? This is atomicity, and this is one of the most important features of relational databases. Even not, it does not mean that non-relational databases do not provide that. We are just talking about relational databases at the moment. Right? So atomicity is one of the most critical properties of any relational databases that is out there. Now, I'll give example from a non-financial domain to make a very clear understanding of it. So let's say if I'm building a social network, and in social network, what I would want to do is I would want to, whenever a user publishes a post, I want to create an entry in the post table, and in the statistics table I have total post. I want to do a count plus plus of that for that specific user. Right now I have two updates. First is insert, which is changing something in the database, inserting the row in the post table. Second is update, where I'm updating the total post of that user. Now what happens if I don't wrap this in a transaction? So let's say if my first statement ran and before it could execute second statement, my machine crashed. What would happen? I would have an entry in my post table, but my counts would not have been updated, which means that it would say that actually this user has, let's say, 5 posts, but my count still says 4 posts. So when someone goes to the profile, they would say, oh, total 4 posts, but when scrolls would find 5 posts. This is inconsistency. We don't want that, right? We want strong consistency of data. We want atomicity, that if it happens, both of the statements execute, either none of them does. Right? This is what relational databases provide out of the box. You just have to wrap your statements within the transaction. So you say transaction start, and then you write your statement, and then you say commit. Right? When you say commit, both of them would take its effect, otherwise none of them would. This is atomicity. No matter how many statements you provide, either all of them takes effect or none of them takes effect. This ensures that it would never happen that one of them took effect while others did not even get chance to execute. This is a brilliant property, especially for financial systems. And now you see why financial systems need it, because assume that you are moving or you are transferring data from A's account to B's account, and amount debited from A, but before it got credited to B, my system crashed. What would happen? Money just vanished, right? That cannot happen. That's why atomicity is very important property, and relational databases through their asset transactions provide that. Second is consistency. Now in financial system, it is very important to have your data in a very consistent state, which means that, for example, I should not be allowed to transfer money from one account to another in a situation where, if let's say I only have $100 in my account, I should not be allowed to transfer $200 to the users, right, to another user. Now this is consistency. No matter what happens, my database always moves from one consistent state to another consistent state. The way relational databases give you this is through constraints. You can define constraints on relational databases. Some are called check constraints, some are called foreign key constraints, and whatnot. So there are many, depending on your favorite database, MySQL, Postgres, Oracle. Go through the documentation and see the different kinds of constraints they provide, and when you use them, you ensure that no matter what happens, your data will never go in an inconsistent state. Some examples: constraints, cascades, and triggers. Now I'll just brief you about what cascades is. So cascades are very interesting. Cascades suggest that if you delete a particular row, you want to delete everything associated with it. For example, let's say I have a foreign key relationship between two tables. One is parent, another is child, right? If my parent got deleted, let's say, let me be a little more specific. Let's say my parent table is users table child table is posts table, right? So whenever a post is created, the post is created for a particular user, that this user published a post. Now, if I delete my user's entry, one of the user's entry, then all of this post for that were written by that user are now orphan. So cascades, what they do is, if your parent gets deleted, all the children gets automatically deleted. You don't have to write explicit delete for that. But if you'd want to, you can just define a cascade on cascade delete, which would delete the other stuff. The child, when the parent gets deleted, the child automatically dies off, or they are deleted there. This is such a beautiful feature, because what it would ensure is you don't have to make your application logic complicated. You can just rely on your database, because your database would do it within a transaction without you having to worry about anything, right? Triggers are something similar. Triggers, what they do is, when you specify a trigger, that on update trigger this, and on trigger you specify what you need to do when something else happens. So you can invoke a function, you can write a SQL statement that, hey, when a particular entry gets updated, update this particular part. I'll give an example, live example on that. Like, whenever I create an entry in the post table, I want to do count plus plus. You can also implement this with triggers. You can also wrap it in a transaction. We typically prefer wrapping it in a transaction because it's your business logic you have under control. Otherwise, when you write triggers, it's very much specific to databases, right? So people typically prefer writing transactions and putting those business logic there rather than triggers. But you should know what constraints are, what cascades are, and what triggers are. In case you are unaware, just go ahead and implement, prototype it. You'll have much deeper understanding. But this is exactly what I've explained, and this is what happens behind the scenes, right? Okay, now this is what consistency was all about. Now, next is durability. Imagine in financial system, you cannot just say, hey, my data just vanished. You cannot do that, right? Because this is where, when you say that, hey, this transaction is quote unquote committed, no matter what happens, no matter if your machine crashes, so long as your disk is there, your data should be durable. Your data should not get deleted, or sorry, your data should not just vanish out of the blue, right? Your transaction, when your transaction commits, your changes should outlive the outage. Durability is one of the most important feature of almost any database, because they give you that guarantee. Especially when I talk about relational database, they give you this guarantee that when you commit a transaction, that commit is actually being written on the disk. No matter now what happens, except someone just drills the hole through the disk, your data would still be there. This is what durability is all about. And the final one, which is the most important, most interesting one, is isolation. So we learned about transactions, right? Transactions, you can specify multiple statements. Now, when your relational database is running, it's not that at one time only one transaction is happening. At one time, multiple transactions can run. Now, when multiple transactions are executing at the same time, how much of transparency of one transaction should be visible to other is defined by isolation. Now, the worst case, you will say, hey, when one transaction is running, I should not be running any other transaction. This is what serializable isolation level is all about. There are 3 other isolation levels. It's little out of scope, but would recommend you to just go through it. Just a Google search away, but just understand this part on what isolation is all about. When I say isolation, it implies that how much of details of one transaction is available to other transaction, right? So for example, if my one transaction was running this 1, 2, 3, 4, 5 statements, my second transaction was running this 3 statement. Let's say these 2 are happening at the exact same time. Should the changes happening in this 3 statement be visible in this transaction or not? This is what isolation is all about. Depending on, there are 4 isolation levels. Each one of them makes it more stricter than other. Some says it's totally there, some says it's after committed, some says it's not at all, and whatnot. Little out of scope, little specific to database, but you'll get an idea. The idea of isolation level over here is purely how much of transparency from these statements of this one transaction be there on this other transaction, right? This is isolation. So when multiple transactions run at the exact same time, Now, how much of data of one is available to other? I'll give an example just to clarify that. If let's say my transaction one wrote a data into a particular table. Let's say there was a table in which there was a column whose value was updated to 10. But transaction has not yet committed. Now the value that was updated was through this update statement. Now when transaction 2 ran and it read the value, should transaction 2 read 10? But if transaction 1 is not yet committed and transaction 2 reads 10, then transaction 2 becomes inconsistent, right? So you can configure this. These are isolation levels, FII. These are isolation levels, and how much of isolation you want transaction 1 to be from transaction 2, right? So should you allow this 10 to be read by transaction 2 or not? This is what our isolation level defines. This is how your database arranges the transaction such that it maintains that isolation between them. So there are 4 very common isolation levels, but databases can choose to implement others. Just a Google search, just Google search isolation level in relational databases, you'll find a bunch of them. Right? You'll find 4 of them, 4 most common. Other databases choose to implement few here and there, but I would recommend you to play around with it and see how it behaves. Right? Okay. This is about isolation. In most cases, let me talk a little more practical. In most cases, you don't tune the isolation level. Most cases. You go with something called as repeatable read, which is fairly almost standard practice. When you start your MySQL server, that is the default one that it starts with. And in most cases, you don't have to change it. Most cases, right? In some high throughput application, in some use cases, you do change it, but it's not so critical about it, right? You should definitely be aware of what isolation levels are, just a Google search away, right? Okay. So relational databases are there to answer these, or are there to provide you with these 4 amazing guarantees: atomicity, consistency, isolation, durability, right? Now you get this 4 thing. When you get this 4 thing, you choose, when you pick a relational database, you pick one because you want ACID, because that's the highlight of it, right? So you need to have a very detailed understanding of what ACID is all about, right? So what I would recommend is do this exercise, because theoretical knowledge, it's okay, but having that hands-on experience makes a lot of difference. So what I would recommend is do this very 3 simple thing. First, set up a SQL database, be it MySQL, Postgres, pick your favorite, right? Create a schema for a social network, like user, post, profile photos, following, stats, and whatnot. Go in the complexities that you would want to dive deep into, right? And try to model relationship between them. Try to model constraints within them, right? Once you do that, so this would help you build an understanding on how relational databases are modeled. Go through Google, search it, you'll find some schemas, you'll find something, but explore it on your own, right? Go through that struggle, go through that grind and understand it in depth. And once you do this, once you have the schema, at least have your users and profile tables handy. Users is your authentication users table and profile is your detailed profile that we typically have. Now what you do to understand transactions, what I would recommend is you insert the data in users and profile in one transaction and see what happens, right? And when you do it, just when you write that transaction, kill your process in between and see how your database reacts to it. Right? It's very fun. When you do it, you just have to log it to MySQL console and fire those statements. Start transaction, insert this, and then you kill your database and then see how your database reacts. Is any inconsistency in your data or not? If there is, why there is an inconsistency in data? If not, then you understand how transactions are working, right? Highly recommend you to go through this. You'll have quite a fun when you go into those implementation details of it. Right? So yeah, that is all what I wanted to cover about relational databases. And I hope you found it interesting. Hope you found it amazing. That's it for this one. I'll see you in the next one. Thanks, Zeta.